So this is 4.3. We're starting the 4.3 handout on linear independent sets and bases. This video is just a brief introduction to 4.3. The bulk of 4.3 is presented in an actual class lecture video that was preserved from an earlier semester. But I think the video starts on page 2 of the handout, so let's just work our way through page 1 on this brief introduction. So in 4.3, we're actually just going to start by carrying over a lot of concepts that we already talked about in chapter 1. In chapter 1, we applied these concepts to Rn spaces. And these same concepts will carry over to abstract vector spaces. So we're going to just repeat them in the context of an abstract vector space. So first of all, linear independence. So let V be any vector space, and a set of vectors V1 through Vp is said to be linearly independent if the equation C1V1 plus C2V2 down the line to CPVP equals 0 has only the trivial solution where each one of the weights C1, C2 through CP has to be 0. That's the only solution to that equation. Then the vectors are said to be linearly independent. Sometimes we'll just say independent for short. The equation above has p variables, C1 through CP. That represents scalars, right? The linear combination, C1V1 to CPVP, represents a linear combination of V1 through Vp. If the set of vectors is linearly independent, then the only way for a linear combination of those vectors to equal the 0 vector is for each one of the C1 through CP scalars to be equal to 0. A set of vectors that is not linearly independent is said to be linearly dependent. If V1 through Vp is a linearly dependent set, then there exists scalars C1, C2 through Cp, not all 0, so at least one of them must be non-zero, such that C1V1 plus C2V2 down the line to CPVP will equal 0. That's called a linear dependence relationship, where at least one of the C1 through CPs is not 0. Theorem, just for the record, I'm kind of repeating things here that I think we know about Rn. These same ideas will be true about an abstract vector space. So any set containing the 0 vector is a linearly dependent set. Second point, any set of just one vector is linearly independent as long as the vector in that set is not 0. And finally, any set of two vectors is linearly dependent if one is a multiple of the other. Otherwise, they are independent. Again, these ideas from chapter 1 carry over. And I am actually going to stop here at the end of page 1 of the handout, because the video lecture portion starts on page 2, and I'll let you watch me in person in front of a class.